In this video, we continue our lesson on 4.1 with balancing chemical reactions. If you go to the problem set for 4.1 and move down to about halfway through the third page, we have word equations. This is still part of 4.1, and we need to learn how to turn these word equations into balanced chemical reactions. If you go to your periodic table, let's go ahead and review our nomenclature rules, which is just the fancy word for naming chemical compounds. Here are the rules for naming ionic compounds, and then we're also going to review our rules for naming covalent compounds. So keep your periodic table handy as we're going over these rules here. For ionic compounds, they are named by naming the cation first, then the anion, and then you change the ending of the anion to "ide," and we do not use prefixes. If there is a variable charge cation, meaning a cation or a metal that is from the transition metal box on the periodic table, these atoms or these ions make different charges, sometimes a +1 or +2 or +3. Each one is different, and we can't predict which ion it's making just by looking at the periodic table. So then we need to use a Roman numeral to denote the charge on the cation. So let's go ahead and do a couple of these practice. For calcium, or CaBr2, we named the cation, calcium, and then named the anion, bromide. And we do not use prefixes. So we do not say calcium dibromide because calcium is always a 2+ charge and bromine is always a -1 charge. Therefore, there's only one ratio, a 1:2 ratio between these two elements that makes a neutral compound that exists. The next one is potassium sulfide. The Fe2O3 is the one that's a little bit tricky. Iron is a transition metal, and so sometimes it can make different charges. To figure out what charge it's making in this compound, we look at oxygen. Oxygen is always a -2. So that means we have a total of -6 from oxygen. The two iron atoms need to equal up to +6 in order to neutralize the charge. Therefore, each iron is a +3 charge in this compound. Therefore, we would name this as iron with a Roman numeral 3, and then you just say oxide. The 3, of course, does not apply to how many iron atoms there are because we don't have 3. We only have 2. The 3 is because iron has a 3+ charge. Iron is 3+ in this compound. Go ahead and pause and see if you can figure out the names for each of the next 3 examples. Here are all of the answers. Now let's review our covalent compounds. For the covalent compounds, they are not made with charges, so we could have any type of ratio between two non-metal elements. There's a clue there. Covalent compounds are only made with non-metal elements, whereas the ionic compounds are made with a metal and a non-metal. So let's go back to the covalent compounds. This N2O4, there's also a possible ratio of just 1 nitrogen and 2 oxygens, so NO2 exists, N2O exists, N2O5 exists. You can't call them all nitrogen oxide. That would be very confusing. They're all very different chemical compounds with different properties. So we need to use a Greek prefix on the first element to tell us how many you have of that element. Then you also put a Greek prefix on the second element, and then you change the second element's ending to "ide." Our Greek prefixes are on the periodic table right here. So use all of these to figure out what prefix to use for the specific number. Note that tetra is 4. We don't use quad for 4. So we would name this, the N2O4 is dinitrogen tetroxide, tetraoxide. You can say tetraoxide or tetroxide. Typically we do drop off the A in the tetra prefix. The next one is triphosphorus heptoxide. So here's the answers. Our exception here is that you never use the mono prefix on the first element that is listed. So when you have only one of the first element, as in carbon dioxide, we don't say monocarbon dioxide. You just leave off the mono prefix and you say carbon dioxide. However, you do use the mono prefix when you have only one of the second. So we'd say nitrogen monoxide for NO. We're going to learn some new nomenclature here, and these are for acids. We will learn more about acids and bases in our chapter on acids and bases later on, but here we are going to just learn how to name them. The ending on the anion of the acid changes depending on what it was originally. So acids always have a hydrogen ion with an anion. By definitions, acids donate a hydrogen ion. They donate or give up or lose the hydrogen ion. So of course an acid must have a hydrogen to begin with in order to donate it. We will reference this slide to figure out the endings as we do our examples. So let's go first to the periodic table though, and you can find the acid nomenclature rules are on the far left-hand side on the back. Follow this box here as we are going through our examples. There are two different types of acids, binary acids and oxyacids. A binary acid has hydrogen plus one single element because bi is a prefix for two, so you would just have a total of two elements. So let's look at our first example for acid nomenclature. Hydrogen plus the chloride ion with a negative charge makes an acid, HCl. We use the hydro prefix. Then we name the anion, which is chlorine, but we change the "ide" ending to "ic." So HCl is named hydrochloric acid. Always add the word acid at the end of all the acid names. If you had a single element fluorine to make an acid like HF, this would be named hydrofluoric acid. Or if we had something like HBr, we would name this as hydrobromic acid, and so forth. Follow that pattern for when you have hydrogen and only one other element in your acid. Acids can also be made with a negative polyatomic ion with a hydrogen ion. Here's an example. Hydrogen plus the nitrate ion makes HNO3. For these acids, let's go to the periodic table really quick. The periodic table here calls them oxyacids. We don't use the hydro prefix. So see how it's crossed out here. We don't use the hydro prefix. Of course, the acid still has hydrogen in it, just the name doesn't have the hydro in it. So we're just going to go straight to the polyatomic ion name, which is nitrate. If the polyatomic ion ends in ate, like it does in our example, then change the ending to ic. So this is called nitric acid. And if the polyatomic ion ends in ite, ite, you would change the ending to us, or ous. Let's go back to the slides. Here's another example. Nitrite, NO2-, makes an acid with hydrogen ion. What is the chemical compound and its name? So we have H plus NO2-. So here's the chemical compound, HNO2. Hydrogen has a 1+ charge, and nitrite has a 1- charge. Therefore, we just need one of each to make a neutral compound. Now, because the nitrite ends in ite, we're going to change the ending to ous. So the name is nitrous acid. Of course, always add the word acid to the end of the name. Let's do the next example here. What is the name and chemical formula for the acid that carbonate makes with hydrogen? So let's find carbonate on our polyatomic ion list. Remember that you should have this list handy and be very familiar with many of these so that you recognize them. You can clarify during a test or a quiz exactly what charge and what it is made of. Here it is carbonate, CO3 2-. In order to make an acid with CO3 2-, we need to add some hydrogens to this. Hydrogen has a 1+ charge. So in order to make a neutral compound, we're going to need 2 hydrogens. We're always going to write the hydrogens first in the acid. The hydrogens usually lead the chemical compound in an acid. So here's our chemical compound, H2CO3. The name is going to come from carbonate. So if you look at your rules for the polyatomic ions that are made with hydrogen to make an acid, we don't use the hydro prefix. We're going to start with the polyatomic name, carbonate. The ATE ending is changed to ic. So, and we pronounce this carbonic. And then, of course, add the word acid. So carbonic acid is H2CO3. All right, another new nomenclature for today is bases. Bases, the way they are named with these rules, they are 1,000 times easier than acids. We treat bases as if they are ionic compounds. So I didn't even add the rules for these bases to the periodic table because you can just follow the rules for ionic compounds. Bases are formed with hydroxide, OH-, plus a cation. So let's look at our polyatomic ion list. Hydroxide is the top of the second column. Hydroxide is a polyatomic ion, OH with a 1- charge. Therefore, it's going to make a compound with a positively charged cation. So we can name this with just naming the cation, then tack on the word hydroxide because every base has hydroxide. Of course, there are some exceptions, but for now, every base has a hydroxide. So NaOH is named sodium hydroxide, and that's it. It's as easy as that. Of course, if the cation in the base has a 2+ charge, the base will need 2 hydroxides in order to make a neutral compound. We still name it the same way, barium hydroxide for BaOH with a 2 on the outside of the parentheses. We do not say dihydroxide because we always know that barium always has a 2+ charge. So we must have 2 hydroxides in order to make it neutral. We don't need to clutter the name with the word di in the name. There is no other ratio between barium and hydroxide. So again, don't use prefixes when naming the bases. Here are a lot of examples of common bases. LiOH is lithium hydroxide. KOH is potassium hydroxide. MgOH with a 2 on the outside of the parentheses is magnesium hydroxide. So let's go back to the original lesson, or the original content for this lesson here. We need to turn these word equations into balanced chemical reactions. Write a balanced equation for the reaction of molecular nitrogen and molecular oxygen to form dinitrogen pentoxide. So this is the way we put this together in a chemical reaction. We have molecular nitrogen and molecular oxygen. Whenever it says to form or to yield or to produce or to create or something along those lines, that is your clue to add the arrow. Now we're going to write out the products, and we're given dinitrogen pentoxide. This is why we needed to review our nomenclature rules. If there's prefixes, that must mean this is a covalent compound. Di is the prefix for 2, so we have 2 nitrogens. And penta is the prefix for 5, so we have 5 oxygens. This is all one compound. Do not split them up. All right, so now that we have our subscripts correct, whenever nitrogen and oxygen are completely by themselves in a chemical reaction, we have to put the little subscript 2, and that is because they are diatomic elements, and I'll talk more about those in a moment. Let's balance this chemical reaction. We have nitrogen and we have oxygen. We have 2 nitrogens on the left side and 2 on the right side. We've got 2 on the left side for oxygen, but 5 on the right side for oxygen. So if we change our coefficient to a 5 here and a 2 here, we now have 10 oxygens on each side. We have unbalanced the nitrogens so that we now have 4 on the right-hand side, but that's an easy fix. Add a 2 to the first chemical compound of N2, and we now have 4 nitrogens on each side. And that is your finished answer for this type of question. Try this example on your own using our new naming rules for hydrochloric acid, and notice that sodium hydroxide is a base. So pause and work this out before moving on to see the answer. So hydrochloric acid, if you use your proper names, we have HCl. Sodium hydroxide is NaOH. And it says they neutralize each other in a reaction, producing, that entire phrase turns into your arrow. It produces sodium chloride. Following your ionic compound naming rules, we can see that sodium chloride is NaCl and water. Write and balance the chemical reaction. When you count up all the atoms, we have 2 hydrogens on each side and 1 oxygen, 1 chlorine, and 1 sodium on each side. So this reaction is already balanced the way it is written. Here's another example. So we just found out what carbonic acid is in a previous slide. Hopefully you were taking notes, so you can just go back to your notes and use that chemical compound for the acid. Or you're just going to go straight to your naming rules for acids to refigure out what carbonic acid is. Pause and solve this problem before seeing the answer. So if you're looking at carbonic acid here, we can see that because we don't have a hydro prefix in the acid, so you can see some acids have the hydro prefix, others do not. Because we don't have a hydro prefix, we know that carbonic acid comes from a polyatomic ion. Now let's move backwards through all of this. So because the ending is ic, then we know that means the ending originally came from 8, so carbonate. Go over to your polyatomic ions, and we see that carbonate is CO3 2-. So we have an acid with CO3 2-. We know that we need to add 2 hydrogens because each hydrogen has a 1+ charge. Now H2CO3 is a neutral compound. So here's our carbonic acid, H2CO3. The problem says that it decomposes to form. That just means you have your arrow is next. It forms carbon dioxide, CO2, and water. If you count up all of your elements, you have 2 hydrogens on each side, 1 carbon on each side, and 3 oxygens on each side. So this is also balanced the way it is written. Here's our next example. Zinc and iron 3 chloride yields zinc chloride and iron precipitate. Write and balance the chemical reaction. So there's a couple of hints here. In an ionic compound, zinc always has a 2+ charge. And precipitate just means a solid, so don't get thrown off by that word. So we have zinc, and is your clue here to write your plus sign. Iron is Fe, and the Roman numeral means not that you have 3 of them, but that you have a 3+ charge. And then chloride comes from chlorine. If we look at the periodic table, you can see that chlorine always has a -1 charge. Therefore, we know that we need 3 chlorines here in order to make a neutral compound. Don't leave your charges in the chemical reaction because this is a neutral compound. Then the word yields tells us to write our arrow, and it yields zinc chloride. From the hint, we know that zinc always has a 2+ charge. Therefore, we know we're going to need 2 chlorines in order to make a neutral compound because each chlorine is just a -1. And, is our plus sign, iron precipitate. So that just means you have iron by itself. It is iron solid. All right, now we need to balance the reaction. We can see that we have 1 zinc on each side and 1 iron on each side, but we have 3 chlorines on the left side and 2 chlorines on the right-hand side. So this comes with a least common multiple of 6. Therefore, if we put a 2 coefficient here and a 3 here, let's go ahead and count up our atoms. We still have 1 zinc on the left side, but we now have 3 on the right-hand side. We've got 2 irons and only 1 on the right side, and then we have 6 chlorines on each side. So now let's go ahead and just change these these coefficients so that now we have 3 zincs on each side, 6 chlorines, and 2 irons. In summary, acids have a hydrogen in the chemical compound, and almost always it's leading the chemical formula. So you can recognize an acid by seeing that there's a hydrogen in front. Either 1, 2, or 3 hydrogens, it doesn't matter as long as you have some hydrogens in the front. That typically means this is an acid. Bases always have hydroxide at the end of the formula. So here's your example, sodium hydroxide. Salts is just another word for an ionic compound. In everyday language, we recognize that table salt is NaCl. And it's made with 1 cation and 1 anion. But any ionic compound can be called a salt. So potassium chloride or sodium fluoride could also be called a salt. Let's review this problem and go to problem set 4.1 on the problem sets. So it says hydrogen plus oxygen yield water. Here's hydrogen plus oxygen yields water. However, we need to remember that we should check our diatomic elements box here. Any of these elements, when they are by themselves in a chemical reaction, must have a subscript 2. And that's because they do not exist as a single element by itself in nature. So we put subscripts 2 here, then we can balance by adding the coefficients there. And that is our last example for today.